Hello, good afternoon. Welcome to S-CUBE 2020. I'm Sérgio Lopes, co-chair of this conference, and I hope you are all doing well. In the name of the organizing committee, let me start by thanking all of those who have contributed to make this year's conference successful, namely Natasha from EAI for her support, all technical program committee members for their work on the paper selection process, all authors, of course, for submitting their papers and preparing their presentations. Also, a special thank you to the session moderator, my colleague Sérgio Monteiro, who will be with you after this introduction. Thank you all for your collaboration. One note to say that at the end of the session, I'll announce the best paper award. And that's it. Let's start, and we hope you find the session interesting.
Dear ladies and gentlemen, let me welcome you to the EAI S-CUBE 2020 conference held in this virtual interactive setting. I'm Elena Davidova, and I would like to address all of you on behalf of EAI and S-CUBE 2020. I would like to use this opportunity to address the organizing committee, the authors, and all the participants on behalf of all of us here at EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the General Chairs, Sérgio Lopes and Antonio Costa, and the Program Chair, Enrique Santos, together with the whole organizing committee, for their excellent work during the conference preparation. Today, during this streaming, we would like to invite you to participate in the Q&A sessions. During each video, please write your questions about the current presentation into the chat window. After the presentation is done, the session chair will ask selected questions to the author of the presentation in a live conversation. Lastly, I'd like to use this message to invite you to join us again at the EAI S-CUBE 2021. Should you be interested in becoming a part of the next year's conference, please do not hesitate to contact us at the email address below. Similarly, if you are interested in discussing other possible cooperation, a conference, a workshop, or a new event altogether, please contact us at this email address as well. Thank you for your attention and enjoy EAI S-CUBE 2020.
My name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone, I'm Yitong Liu. I'm honored to join the conference and present the paper for you. The topic of my report is an attack-resistant weighted least squares localization algorithm based on RSSI. Here is the outline. My presentation will include these 5 sections. First of all, I will give a short introduction to IoT, Internet of Things, and WSN, Wireless Sensor Networks. As shown in the figure, the basic construction of wireless sensor networks includes sensor nodes, sync node, and data processing center. The sensor nodes collect physical data and transmit them to the sync node. The sync node collects and merges the data and forwards them to the data center. The data center plays an important role in data processing, data classification, and further data integration. In the supervised areas, the WSNs can monitor the objects effectively, while in IoT, more and wider areas can be monitored. Wireless sensor networks have high research value. It has been used in many fields, such as the forest fire precautions, personal health care, mechanical fault diagnosis, and so on. We know that most applications require accurate location information, and the collected information is meaningful only when their location information is correctly designated, and they can be correctly processed only when their locations are known. The motivation of this paper is to ease the tension that the locations of nodes in the network are estimated incorrectly when the nodes are deployed in malicious environment. In this case, the secure localization is especially important. Then we make the introduction to the network model. Before we propose our localization algorithm, I'd like to introduce the network model employed in our paper, including some parameters used here. As shown in the figure, the distance measurements of sensor networks are available based on the received signal strength, RSS. Each node provides the other node with location references. In the presence of the malicious anchors, DI is the distance measurements between the ith anchor and the target node. It can be obtained based on the following formula. When the ith anchor is benign, we use the first part, and when the anchor is malicious, we use the second part of the equation. Where AI is the location of the ith anchor, T is the target node. Ni, following the normal distribution of mean 0 and sigma square as variance, is the noise of the ith anchor. Ui, following the normal distribution with mean mu delta and variance sigma delta square, is the attack component. In the ranging function, we introduced the RSSI-based model. For RSSI-based ranging, the distance between the anchor nodes and the target node can be estimated through the path loss formula. The received power away from the reference transmitting node can be computed as the following equation, where PR is the received power of the anchor nodes, P0T is the transmitting power of the anchor at the reference distance, A is the path loss exponent, and D is the distance of the anchors away from the reference transmitting nodes. Given the transmitting power P0T and the received power Pijr, the corresponding distance EDIJ can be estimated as the following formula. Based on the equation, we know that there exists a nonlinear relationship between the measured distance EDIJ and the received signal power Pijr. In our design, the localization algorithm is proposed based on the following assumptions. First, the network is stable, and the locations of all sensor nodes are not changed after deployed. Second, all anchor nodes are within the communication range of the target node. In other words, the target node can receive signals from all other anchor nodes. In non-coordinated attack environment, the attackers act alone on each captured anchor node, so the target node is unaware whether the transmitting power of the anchor node has been changed. In this case, the received signal power, PIRNC, at the target nodes can be given using the following formula. When the attack does not happen, MI equals 0. We use the first part of the equation, while the second part is employed when attacks actually occur. In coordinated attack environments, the attacker may specify a position which may be randomly selected, or a position that is determined to be favorable to the attacker. In this case, the received signal power, PIRNC, at the target node can be computed using the following formula, where PMIC is defined by the distance between the malicious node, Tmol, and the target node, T. Then we come to the third section, the proposed algorithm. The proposed algorithm can be divided into two stages of operations. The first stage, we remove the detected malicious anchor nodes. The malicious anchor nodes found are eliminated to prevent the false information from being used in localization of the target nodes. In the second stage, the robustness of location calculation is improved. Here's the flow chart of the algorithms shown below. First, we would determine the reference anchor node and the initial location estimate by a quasi-Newton method. Then we use the power difference information of the reference anchor node to calculate the reference difference interval. Then, we take the power difference values as the test samples and carry the sequential probability ratio test, SPRT, on remaining anchor nodes. Finally, we'd locate the target nodes with all benign anchor nodes by weighted least square method. Let me explain it further. The first step is to determine the reference anchors. Assuming there's no malicious anchor node, the BFGS algorithm is iteratively used to search the least square solutions. The residual sum of all anchor nodes is taken as the objective function. According to the BFGS algorithm, we have the following equation, where k denotes the number of iterations. Bk is approximately positive definite matrix of the inverse of the Hessian matrix, and del f, tk, represents the total gradient corresponding to the location of the kth iteration. The update formula of the location estimate tk plus 1 is shown below. The second step is to calculate the reference difference interval. The reference anchors are utilized to obtain the initial estimate location, TF, of the target nodes via trilateration. The transmitted power, PIJT, can be approximately computed as follows. Given the distance measurements EDIJ, the jth transmitting power of the ith anchor can be approximately inferred with the following formula if the measurement noise is ignored. Therefore, the power difference value Dij can be calculated as below. The power difference values are taken as examples. Suppose the reference anchor node is an individual, then the mean value Di bar and the variance Si squares of the ith individual can be calculated. In this equation, the P means the number of packets transmitted. Averaging the mean values of the different individuals, we can obtain the mean value of the total samples with the following formula, where R is the number of reference anchor nodes. The variation SE squares of the mean value Di bar between individuals can be expressed here. The variance SA squares between individuals can be expressed as the following equation, where N is the total number of samples. Based on the analysis of the SI square and SA squares, the variance of the sample population can be expressed as the following equation, where MH is the harmonized mean of the measurements. Based on the above analysis, the reference error interval of the power difference between the reference anchor nodes can be calculated given the significance level epsilon, where Z 1 minus epsilon divided by 2 is the upper quartile of 1 minus epsilon divided by 2 of the standard normal distribution. Before testing, we establish a Bernoulli random variable Zij for the difference information Dij of the remaining anchor nodes, which is given as the following equation. To find the probability of Dij exceeding the reference difference interval as P, then the probability of Dij within the reference difference interval is 1 minus P. We have the two hypotheses. They're set as H0. When P is less than P0, the anchor is benign, and H1. When P is larger than P1, the anchor is malicious. Here, the P0 and P1 are the values predetermined. The selected benign anchor nodes are relabeled as 1 to H, and the corresponding coordinates are denoted as the tuple of xi and yi. I start from 1 to H. The variance of the squares of the distance measurement can be calculated as the following equation. This variance vector, EDI square, is used as the standard to measure the reliability of anchor nodes. Locate the target nodes with the method. The weighted least squares, in the absence of any information about the noise, attack, and the proportion of malicious anchor nodes. The reciprocal of the square variance of multiple measurements is used as the weight to enhance the robustness of the algorithm. Then the weight matrix can be defined as W equals the diagonal matrix of W1 to WH. we use the modified version of weighted least squares to make the final calculation. The final estimate of the target node location can be calculated here, where the matrices W and A and vectors T and B are given as follows. Now that we performed many simulations, ran programs coded with MATLAB, I will report the results. We considered a two-dimensional localization, in which all anchor nodes in the region are randomly distributed. The proposed algorithm is to be compared with other state-of-the-art secure localization methods, including the gradient descent, the weighted least squares, and the least squares. The parameters setting in the experiment is summarized in the table. They were also used in literatures. Figures 1 and 2 show the localization error of different algorithms with different attack strengths, here denoted with deviation sigma ATT, under different measurement noises sigma. Figures 1 and 2 show the localization performance at sigma equals 2 dBm and 6 dBm. As is shown in the figures, we see that the performance of the proposed ARWLS algorithm in positioning is better and more stable than any other algorithms. As sigma ATT increases, our proposed algorithm can still get high accuracy. This figure shows localization errors with different percentage of malicious anchor nodes. The proposed algorithm performs better than the other algorithms under different number of attack nodes. This figure shows localization error with varied number of packets transmitting in the network. With the increase of the number of packets, the SPRT mechanism in our proposed algorithm performs better than the other algorithms, leading to a lower localization error. Now, we'll make the conclusions. The malicious anchor nodes may tamper transmitting power and launch non-coordinated or coordinated attack to the network. Traditional localization methods do not consider the case of anchors under attack. Hence, we propose this algorithm, attack-resistant localization algorithm for WSNs. The two-stage localization algorithm is proposed here. The first stage is to use the quasi-Newton method to determine the reference anchor nodes. The second stage is to use the SPRT test mechanism to further screen the malicious anchors. And the weight matrix is introduced and used to improve the robustness of localization. And from the result, we could see that the proposed algorithm outperforms any other algorithms of interest. Here's the reference. My presentation is finished. Thank you very much.
Hello everyone, good afternoon and welcome to the presentation of MOBIUS, Smart Mobility Tracking with Smartphone Sensors, a study that has been conducted at the Open University of the Netherlands. First of all, let me introduce myself. My name is Daniele Dimitri, and together with my colleagues Khalil Asiraf, Kevin Trebing and Stefano Bromuri, we conducted this study at the Center for Actionable Research of the Open University of the Netherlands. This presentation is structured as follows. We'll first present the background of the study, then we will introduce some of the related works in this area. We will list the functional requirements that stand behind the MOBIUS architecture. We will then show the system architecture consisting of data collection, data storing, and corresponding collected data set, data annotation, and data analysis. That resulting into the results that we gather from the evaluation of the MOBIUS prototype and corresponding discussion and conclusions. MOBIUS stands for Mobility for Urban Sustainability and is a project that is part of the Safe City program of the Open University of the Netherlands. The problem identified by the municipality of Heerlen is that they don't have reliable data about how people move around the city. So in order to monitor that, they use paper-based questionnaires in which the chosen citizens, a part of this study, they have to self-report at the end of their day where they have been and which mode of transportations they have used. Of course, you can imagine this is not very efficient because it's very prone to all kind of errors of evaluation, how the people are using the mode of transportations. In this sense, MOBIUS aims to actually replace the questionnaires with a mobile application, and to classify this mode of transportation would use neural networks that gather the sensor data, uses the data from the device and the labels collected by asking the users to self-report whenever the journey happens, to self-report which mode of transportation they are using. The related work in this area has used different methodologies and also different data. And the first study date back in 2006, where phone signal coverage was used to classify between stationary, walking, and driving, achieving 80 or 85% of accuracy. Then the proximity to bus stops and GPS data was also used, achieving 93% of accuracy in 2011. Only recently, 2013 and 2019, accelerometer of the cell phone was used to classify between stationary, walk, bus, train, metro, and tram, achieving in 2013 80% and 2019 95%, using a convolutional neural network. Lastly, Zhao in 2019 proposed the bidirectional LSTM using a multi-layer perceptron that uses the gyroscope readings, accelerometer and gyroscope readings on the classes stationary, walk, run, bike, bus, and subway, achieving 92% of accuracy. Our classifier, our approach, is inspired by the work of Liang in 2019 using a convolutional neural network. First, before developing the prototype, we set some functional requirements that relate first to the data collection. So to the fact that the MOBIUS application should be able to collect data for long periods of time,
for example, for the entire day. And this data collection should happen in the background so that the user doesn't close involuntarily the application. And the data collected should be sampled for 60 Hertz, so 60 updates per second, that for accelerometer and gyroscope, while GPS coordinates should be sampled every 10 seconds. These ideal measures were found in the literature. And of course, the data gathering should not drain the battery usage of the phone, and this was quite important requirement for the app. Then the second functional requirement have to do with the data storing, to the fact that the stored data should be in some kind of compact format, and we store them into zip format, and should be able to actually be transferred to a server, be pushed to a server from the client, and without killing the Wi-Fi network. And third, the functional requirement on the data annotation, the fact that the user should be involved in annotating their own datasets, and therefore self-report the mode of transportation. And therefore, the user can activate different toggles for each mode of transportations. And the user annotations should be editable afterwards, because we also suppose that the self-reports are prone to some errors. The fourth functional requirement relates to the data analysis and the fact that the suitable representation for machine learning needs to be found, especially considering multiple sensors. And finally, the fifth requirement has to do with the user privacy and the fact that the GPS coordinates are quite sensitive data, and there should not be considered in the classification. And the user, if the user wants, can also deactivate the GPS coordinate tracking, as it is not fundamental for the final classification, but perhaps only to revise the annotations later on. This is an overview of the system architecture of the MOBIUS system. It consists into 4 main components. The first component is the MOBIUS client, which is an Android application, and that actually is responsible for collecting both sensors and annotations. And the second component is the MOBIUS server in the middle, that is actually responsible for storing the data from the different devices, from the different clients. Then the third component is the visual inspection tool, which is third-party component that we used for editing the annotations of the recorded sessions. And then the sharp flow component that allowed us to actually train the model on the recorded datasets and use this model for classification. The first part, as I said, is the data collection, and it's consisting in the MOBIUS client, which is a mobile application that we developed in Android. And this application uses 2 flow of information. The first one is actually collected automatically, are the sensor data, and we said we collect both accelerometer and gyroscope of 60 Hertz, so 60 updates per second, and we collect also GPS every 10 seconds. The GPS, as I said, has a checkbox that can be deactivated. The user starts and stops the MOBIUS app, and the MOBIUS app runs as a daemon in the background. Then the other flow of information comes from the self-reported annotations, where the user can activate the toggles corresponding to the annotations of walking, running, biking, train or bus, and car. And these annotations should be done at the beginning and at the end of the journeys. And at the end of the day, as is shown in the screenshot in the right, the user can hit the upload button and upload the recorded session during the whole day and corresponding annotations into the server. The second part of MOBIUS is the MOBIUS server, which is responsible for storing the data. So each session, as we said, it's stored into a zip folder, first stored locally and then pushed to the server. And when the user hits the upload button, the zip folder is transferred to the client, to the MOBIUS server. And the MOBIUS server implements a RESTful web service that was implemented with Python Flask. And each session folder is composed by 3 CSV files containing data from the accelerometer and gyroscope, the GPS, and the annotations. Along with the CSV data format, we also use the JSON data format, MLT JSON, which is the format used by the visual inspection tool that we use for the annotation and revising the annotation of the user. We will show in the next slide. The visual inspection tool is indeed a tool that allows to load recorded multimodal sensor sessions and is able to visualize to the researcher the trajectory, and the researcher can actually see if the corresponding annotations if the annotations correspond to the sensor data. So specifically looking at the in this particular case at the speed, and the researcher can check whether the user was actually using the car or walking or running, and check if, for example, the user forgot to actually detect, to actually self-report if was walking or if was driving. The dataset that we collected in the user pilot was collected from 4 users and resulted into roughly 47 hours of recording. And the dataset was pre-processed and used as input for training the neural networks. As we said, we only considered accelerometer and gyroscope, the 3 dimensions of both. So in total, we consider 6 attributes. We used a sliding window approach of 512 data points that correspond roughly to 8.7 seconds, and we shifted this slide window every second, and that resulted into about 168,000 samples that are shown here in the table on the right. We showed the distribution of these samples per each class and the proportion that each class has in the total. We also, to pre-process the data, we removed from the accelerometer, we removed the gravity as suggested in the literature. We also applied smoothing at each sensor stream. And to try also different setups, we calculated also the accelerometer magnitude, which is some kind of measure that somehow combines the 3 dimension of the accelerometer. For the data analysis, we developed a component called SharpFlow, which implemented different models. The main one that we used is the one is shown in the figure, is the convolutional neural network model. This model is composed by, this network architecture is composed by 6 one-dimensional convolutions with max pooling, followed by a hidden layer and a final output layer. The first convolution has a kernel size of 15, while the next 2 have a size of 10, and the last 3 have a size of 5. Following every convolutional operation, we apply the ELU activation function, and followed by a max pooling operation. Then we flatten the signal and we feed this signal into a multi-layer perceptron that has 200 neurons as an input, as a hidden layer, and 6 neurons corresponding to the target classics. The total amount of trainable parameters in this convolutional neural network is about 230,000 trainable parameters. We also developed a bidirectional LSTM, which consists of 2 layers with 64 neurons and 32 neurons, and a total of 80,000 parameters. And we also considered the 2 dummy classifiers. The first one, the most frequent classifier that predicts the label with respect to the training sets class distribution, and the second one on that always predicts the most frequent label. When it comes to training, we train the CNN with 200 epochs with a batch size of 1024, and we used ADAM optimizer. We also used the early stopping if the validation loss did not decrease for more than 30 epochs. The lowest validation loss on the training run was the best performance model chosen to be assessed on the test set. The code of SharpFlow is available at this address and available in GitHub. The results that we got are shown in the following table. As we can see here, the convolutional neural network and the bidirectional LSTM performed way better than the dummy classifier. So they outperformed the dummy classifier by a big margin. In general, LSTM and CNN basically performed way better, especially with respect to the walking, running, stationary, car, train and bus, and biking. We can also see that the convolutional neural network that uses combined accelerometer and gyroscope does not perform way better than the one using only accelerometer. That means that somehow the gyroscope is not as informative as we thought. The bidirectional LSTM doesn't perform as good as we thought in the literature, and also the CNN using only the magnitude of the accelerometer also doesn't perform as good as the ones using the 3-dimensional accelerometer and 3-dimensional gyroscope. In the discussion that we can draw from these results is that, first of all, the gyroscope sensor seems to have a minor performance impact. Excluding it, that means that we will extend the battery life and also the storage space. Then the bidirectional LSTM does not achieve over the 90% as in the literature, and we thought that this is due to the fact that they in the literature used a smaller window, 2.56 seconds, with a smaller sampling rate of 50 Hz, unlike our longer window of 8.7 seconds and a bigger bigger sampling rate of 60 Hz. In addition, the CNN outperformed the LSTM approach, and we think that is because the CNN can leverage the kernels, the spatial invariant kernels of the convolutions, and these spatial invariant kernels allow to detect the cyclic nature, the cyclic motions of walking, running, and so on. So it's better for detecting these types of activities. As conclusion, we can say that the MOBIUS is a system for smart mobility tracking with smartphone sensors and can automatically classify transportation mode using only accelerometer and gyroscope data. We tested MOBIUS with 47 hours of recorded data, and we achieved 89% of accuracy using a convolutional neural network. MOBIUS presents a scalable also client-server architecture, which can accommodate data from multiple clients, from multiple devices. And one important feature is also that it takes the user into the loop because the user is asked to self-report the mode of transportation. We released all our code open source on GitHub, so you can directly try yourself the MOBIUS app. And we also aware that this kind of applications pose some serious privacy concerns due to the possible surveillance use that can be made. Also, to mitigate privacy concerns, we imagine future applications in which we can, for example, use Android Wear, so the smartwatches, and we want to develop a MOBIUS version for smartwatches that can also use additional modality like the heart rate. And these approaches can be used for human activity recognition, and that can be useful for different use cases. For example, recognizing activities in daily life, or monitoring performance during sports, or also during physical rehabilitation tasks. And to mitigate the privacy concerns also, we can embed the models in the future into the Android app to avoid the exchange of data between the client and the server, so to uploading the data into the server, and to make sure that the classification happens locally into the device. This was our presentation. Thank you very much for your attention. In case you have any question, you can either ask during the question and answer, or you can send an email to the authors. Thank you very much.
Hi everyone. Today I'm going to present our recent work on comparison of multivariable calibration for local state environment sensors. The question that we want to answer from this work is whether the artificial neural network is always the best option when it comes to selection of a calibration method for local sensors. So at the beginning of the talk, I will first talk about the background of the research, and then I will talk about local sensor that we use in this study and its data profile. After that, I will talk about the calibration of local sensors. Then we start our comparison of the calibration methods, which compares two most widely used methods. One is an artificial neural network-based method. Another one is a regression-based method. Then finally, we conclude the talk and discuss our findings. So a bit of research background. And we do this study is a pollution in urban environment we have seen become the largest environment causes of disease in the world today. So to maintain and mitigate pollution levels in cities, having a good monitoring setup is extremely important. The current practice which we will use is using high quality monitoring instruments, which is something look like on the left of the figure. The advantage of using such an instrument is it provides a good and high quality data. But the problem is such instrument can be extremely costly. Individual one can cost up to £100,000. So with this much of cost, we cannot densely deploy such sensors. So the data resolution in terms of the spatial resolution is very limited. Then the alternative solution, which is using local sensor, is something like showing on the right figure. And we see, right, the advantage of using those local sensors are really, we can deploy a large number of them, then they can form a very dense network. So the obtained data in results is becoming a much better with the spatial resolutions. However, the problem with local sensors are their low data quality, and I will show in a second for how they look like. On the left of the figure, we have a box plot of the data, and we have two pairs. ALMA sensor is a local sensor we use, and the reference sensor is a high quality sensor that provides equally good data as the bunky sensor I've just shown you. So we've seen two locations. One is Waco, and another one is city. So Waco is in a relatively mild environment, which is far away from the city center and away from the major roads. And the city center means we have a sensor in the heart of city center and next to a very busy junction. And we see the data of the ALMA from the mild environment shows a large variability in compared to the reference sensor. And this outliers get even worse when those local sensors are placed in a harsh environment like city center, and we see extremely high outliers and strange patterns which we did not observe in the reference sensors. And to get a close look at how they are, and for those city data, we scatter plot the ALMA sensor with a reference. And we see that ALMA sensor got an extremely higher range compared to the reference one, so we even highlight with the different colors. And we see these strange patterns, and this is very difficult to deal with because we're seeing a single value of the ALMA actually maps to a multiple values in reference. It's actually ranged from 0 to 40 versus just a single point. So using the data from this local sensor, this will not help to understand the environment. So the improvement is necessary, and that's down to how we can calibrate those local sensors. And we actually have many different methods for calibration. The very basic ones is just using a univariate calibration. That's just apply a linear function to the parameter of interest. And in this case, we're calibrating NO2. So the univariate calibration is here. We just apply a matrix A if we consider the NO2 as a vertex, as a vector, as a B as a gain. Then we have a multi-parameter, multi-listed square calibration, and that is something on top of univariates because we include more supporting parameters when calibrating NO2. The intuition for using multi-parameter is if some parameters like ozone are related or affect NO2, then if we include such parameter and account for its impact in the calibration, a better calibration result can be derived from. So we're using a linear combination of the multi-parameters, then we're just adding a term onto each other. Then a neural network-based algorithm using a multi-parameter is just building a function related to those inputs. it may not just have a linear combination, but it's just determine how we trained it. Then the result we're showing on the left. The first one is just we shown before. That was ALMA local sensor data versus reference without calibration. And this figure shows we applied the univariate calibration, and we see that we actually scaled the range of the ALMA sensor, but we're still not fixing that strange pattern in the data. And this one is a trial that we did. We obtained the calibration methods using a multivariate calibration in one location and applied to a sensor in a different location. So in this case, we applied calibration. We obtained our calibration equation in a mild environment and apply those obtained function into a sensor in a city center. So which is in a totally different, and we see that a strange pattern comes. Then the last one is we obtain the multivariate calibration in situ. Then we see compared to using a univariate calibration, the linearity of the data becomes way better than without using a supporting parameters. So we've seen a use of the we've seen the benefit of using multivariate calibrations. We've also seen an increased use of a neural network based calibration. Then the question becomes whether the neural network based calibration is always better. Then we start to wonder one that will not be a case. So we start a comparison of the calibration methods. We compare the neural network with a regression-based methods and see and compare them in 3 different ways. We first compare them in a model construction. We think how easy the model of the calibration model can be constructed, and we determine what hyperparameter within the calibration function need to be determined. Then we test their performance by varying a training and testing data set individually. And last, we vary the data characteristics and see how robust those each methods are. Then we show the comparison of model construction. We've seen the artificial neural network. We have a number of hyperparameters to select. And by varying each values, we actually have a different result. That's because once it comes to the optimization algorithm, it may end up with a different Pareto from. That leads to a slightly different optimum. So we've seen a variation of the artificial neural network in terms of results, but the regression one is consistent. Even though the difference between two is not significant, but that is kind of indication if we do not select a good parameters for artificial neural network, we may end up with a higher variation. That is downside of using neural network once coming selects a hyperparameter, because once we are in a process of selection hyperparameters, that will have a direct impact on the final calibration results. Then we start to test when we're varying a training data set, how it would affect the calibration result for both methods. And if we think about this, black ones are the data set we have, and we chunk them into 10 different partitions, with each one being the same size. We use 10 as a testing data set. The reason why we use the same one is we try to fix the testing data as the same one and just vary the training data set. We start to train with 10% using fragment 9, then using 20%, which is gradually increase this. In this way, we preserve the temporal dependency, if there is any, in the training and testing. So in the last one, we have 90% of the data used in training and using a last bit for testing. And we plot the area in terms of box plot, which is shown on the left. The first one is the result of neural network-based methods. The lower one is a regression-based method. From the area distribution, we did not see a significant difference between both and across the different percentage of training data set used. So further investigate that, we plot the mean area, which is shown on the right. So we see this blue ones is a result for neural network with a confidence bar that is 90% confidence. Then the yellow is a regression-based method. And we've seen this for the first one, the difference between the two methods are very small, and even for 20% are very small. But when we gradually increase the training, we start to see increase the difference. And what interesting to us is when we increase the percentage of training, the impact that's introduced by the different training data set is actually bigger if we compare just the two methods, like in 10%. That kind of indicates the variation of a training data set may have extremely large impact for the calibration results, and it may sometimes even bigger than selection of the different calibration methods. After analyzing a training data set, we start looking at how the varying of the testing data set would affect the calibration result. Again, the same data set we used, and here we're using just one chunk as a training data set, and we gradually increase the size of the testing data set. Again, we are adding 3 after 2. In that case, if there is any temporal resolution, we kept. But we can see, since we have very little training data set used, when we start to introduce following chunks into the testing, we may see the distributional shift of the data. And we see the results here. So we plot the errors using a box plot, which is shown on the left. The neural network-based methods were just on this graph, and the regression-based methods were shown on the lower level. And you see when we use a 10%, this actually gets the smallest error because we have a lower outliers and we have a lower box as well. That's true for both methods. And once we introduce 20%, then the error starts getting larger and we see a bigger outliers. And as said, that may be due to since we have a very small training data set, and with increasing a higher, more data in the testing, we might see the distributional shift of the data, then the calibration method may not cope for that changes. Then we start to see the mean errors like we've seen in training data set. Again, the difference between the two methods are very small. Like in 10%, they're almost identical with 95% confidence. And the difference between the methods are very small and gradually doing that. But we see a massive change in errors, the mean errors, when we gradually increase the testing. Again, this funding is in line with our previous funding. Is when we change the size of testing, the impact on the calibration results may be bigger than the difference between the methods. So after analyzing varying the training and testing data, we started looking at how the varying of data characteristics would impact the method. So we have three type of data characteristics used and tested. That's this entire data set. We have, given an example, we have more data than 200 sets, but this is just the indication about what do I mean by training and testing and what's changed. So the constant value, we have a training data set, and just look like this. Then constant value means the testing with just a flat. That is just the value of the mean for the training data set with the standard deviation equals 0. So we use these bits of data for training calibration function. Then we test on this data set. Then drift of the mean means that is what our training data is. And this is the change of mean. So the testing data have a higher mean value, which is 2 times than the mean value, and standard deviation remains the same. So we maintain the same standard distribution of the data. The high variation means the variation of testing data set, which is standard deviation, is doubled, but with the mean remains the same as the training data set. And we want to see how both of methods would cope with 3 types of changes of data characteristics in testing data set. So the first is a constant value, and we know that when we're using multi-parameter calibrations, the previously described the data characteristics can have impact in all parameters. So we apply that changes to each of a parameters, then we're considering the result of the calibration on for NO2. The none means we did not apply anything. So this is used our baseline. So no modification were taken. Then NO2 is the data property of NO2. The testing data of the NO2 were modified according to the constant values, but all the other supporting parameters remains as what it was before. Then O3 is when we calibrate NO2, we only change the O3, ozone, and etc. and so on. And we see that when we change the constant value, we did not see a significant difference across the different parameters we modified. And we've seen a slightly better, in this case, regression-based method outperform the neural network. So in that case, the neural network may not outperform the regression based on the data that we provided. Then we look at the drift of means, which is we change the mean of the testing data set. And we're seeing when we change the mean values of some of the parameters, the error start to differ between the methods. And especially when we change the temperature, we see the error profile start to difference. Without changing that, we see the neural network, the regression performs slightly better than this. And this one, we see a big difference between the neural network and the regression. And that suggests neural network and regression-based method may assign a different weight for a different supporting parameter used. And since the neural network are used just as a black box, we may not easily know how much weight we assign for which parameter, but we can easily interpret those in regression-based method by looking at their coefficient. Then we look at the higher variation, which is changes of the standard deviation in testing data sets. And in this case, we compare with the benchmark, which is haven't changed anything. We haven't seen too much difference apart from the other outliers. That means with certain parameters, it again have issues for overall calibration, but we did not see a significant difference between the methods in dealing with the precision issues. So I think both methods can deal with pretty good for a variation of the standard deviations, but it may not dealing that well for the change of the mean, especially for certain parameters. We've done our analysis, and we can start to make a conclusion. So for the analysis that we've done, we did not see a neural network-based method consistently produce a better calibration result in comparison to the regression-based methods. And we've seen some of cases where the neural network even perform much worse than regression-based methods and shows certain drawback. For example, if we want to interpret which parameter assign two more weights in calibration methods, we could easily check those for regression-based method by interpreting their coefficient, but we may not easily to get that information for neural network-based methods. And the more important finding we have here is the performance of the calibration can be more sensitive to some of the factors, such as size of the training data set, testing data set, or how you sample them, or a selection of hyperparameters. Those are more can have a higher impact on the calibration result than the selection of methods, and that suggests to looking at what those factors are and how their impact to the calibration result can be an important task for a selection calibration method for local sensor. Thank you.
Hello everyone, my name is Nermin Abubakar and I'm glad to present today my research on a feature fusion transfer learning method as a basis to support automated smartphone recycling in a circular smart city. So I'll start with the motivation and research focus. Then I will present the state of the art. I will show the implementation and real test. Then I will end with conclusion, limitation, and future research. So from the title, here we have three different research domains, namely transfer learning included in artificial intelligence, circular economy, and smart city. So this paper addresses the problem of smartphone recycling and applies a feature fusion transfer learning method to classify smartphones without any external information about product designs. So by looking at this graph, we can see from this intersection our interdisciplinary research in cooperation with digitalization and circular economy. We embed this deep investigation in a wider framework of smart city development. So for the interplay of emerging digital technologies such as artificial intelligence, this would support smart city development and CE opportunities, beside the challenges associated with e-waste, bring us to our research question. How can AI, or particularly transfer learning, be applied in order to enable automated smartphone recycling, hence to contribute the development of circular smart cities? Now, what is the state of the art for this automated waste management? I'll put some examples here. Zen Robotics that uses AI system called Zen Brain. So visual data of waste is analyzed and sorted in the real time, but it doesn't process e-waste. Another example is Refund Sorting, which developed an automated system for sorting and grading electronics. It uses sensors and AI to detect the status of e-waste and sort them into different categories: reuse, refurbishment, or recycling. It processes a categorization, but only for trading, either directly or with customers or through digital marketplace. The third example here for Apple company. It claimed that their robot Daisy can disassemble 15 different iPhone models of 200 devices per hour, but it's designed for their own models only. For our contribution, what we can do is a smartphone classification for 14 models with 6 brands, but we cannot do so far. Maybe our future research could, is to include more e-waste devices. To investigate on e-waste recycling, we use case smartphones. Why? Because smartphones play a vital role in our daily life. People use them not only for communication, also for shopping, navigation, entertainment, and many other activities with few screen touches. And the continuous consumption of smartphone contributes to a scarcity of non-renewable resources, since smartphone manufacturers use rare earth elements and other precious metals, and many concerns are raised because about 17 elements needed to manufacture smartphones are finite. So the continuous depletion of these resources is alarming. Moreover, challenges for smartphone classification emerge as their design look very similar recently in terms of shape and size. In our implementation, the computation environment was MATLAB is chosen because it has a suitable deep learning toolbox, which allows us to comprehensively customize solutions by creating, editing, visualizing, as you can see later, and analyzing convolution neural network. We use the Core i5 Intel laptop with 16 gigabyte RAM simply, and we use an Allied Gigi camera for the real-time testing. Here for the data set, it consists of 400 images that represent 14 models of smartphones from six brands. The images are collected from search engines, and in our study we focused on the backside of the smartphones because it has unique features like the logo, camera lenses, and their locations are distinguished. For our data set, we split into 80% for the training set and 20% for the validation. Now, to implement transfer learning means choosing a pre-trained model that leverages the required task as a starting point, then fine-tuning it to achieve the desired results. AlexNet is a large convolutional neural network. It has successfully classified 1 million.2 images with 1,000 object labels. So this abundant data is rich with wide variety of feature representations. AlexNet has been intensively used in many applications as leading model that uses transfer learning because first, it's considered as a deep neural network because it has many hidden layers for nonlinear feature extractors. Second, it has a high performance trade-off because of trade-off between the accuracy and the speed. So thanks to the rectified linear units ReLO function that accelerates the convergence of a neural network, then using saturation function like sigmoid or hyperbolic tangent. Last, it outperformed the other non-deep learning method in the ImageNet large-scale visual recognition challenge in 2012. Therefore, AlexNet is used in our approach. So, technically, building an entire neural network is a challenge even to AI experts. Therefore, rather than reinventing the wheel, we use AlexNet as pre-trained model on a larger scale dataset, fine-tune the model on a new, relatively small training set of smartphone images, and transfer the learned characteristic to classify smartphones. So, using the pre-trained model is not simply as plug and play. We have to understand its architectures and analyze here. So as we can see from this figure, the AlexNet has 8 learned layers. It has 5 convolutional layers from conv1 to conv5, where conv1 to conv5 are basically used to extract the generic features with different colors, texture, and intensity. Whereas convolution layer 4 and 5 extract more refined features, or what we call local patterns, like those with different sizes and shapes. AlexNet has 3 pooling layers. They are usually used to downsample the features to implement faster computation. AlexNet also has 3 fully connected layers. We have FC6 and FC7 are mainly used for features that are more task-specific. This also prevents the model from overfitting during training. For the traditional or the original traditional AlexNet, we have FC8. It combines the previous feature to present the 1000 output classes. So in the last third layer is configured to map to extract features from the previous layers to match the 1000 output labels. Then the softmax layer here acts as the normalization layer. So this step we can use the raw values of 1000 classes to a probability distribution of the time of the image belongs to that class. So the sum of the element of this vector is equal to 1. Finally, the last layer takes the most probability and return the most likely class as a network output or predicted class. So what we do here for the fine-tuning, as you can see, we cut here the last 3 layers. We proposed some modification. Here also we call it like freezing of the last 3 layers by replacing them with fully connected layer, softmax layer, and a classification output layer. This will suit the new training set of 14 models of smartphones, then retrain them all as we have here for the implementation. And for the training algorithm, we use the stochastic gradient descent with momentum SGDM method as a training algorithm because it converges faster towards the lower minima and oscillates less. We set the mini batch size to 20, and we control the early stop when the validation error no more improves to set a trade-off between the training time and the accuracy. So following the training, we evaluate the network performance using the validation set during training. This is an important step to check overfitting. Now we have prepared the 3 previous components, which are training data, network architecture, training algorithm, we are ready to train our network. Now we'll demonstrate different metrics to evaluate the performance, which are the accuracy, loss function. Besides that, the confusion matrix of validation testing. The real-time testing also will be connected later to test the model performance. So when we train the data, we get this test as the accuracy and loss function graph. The accuracy here represents the percentage of the correctly classified trained images during an iteration of the entire dataset. It calculates the root mean square error in the model gradient function. And the error between the predicted and the true non-class is called the loss function. It defines the actual output are correctly predicted. Practically, it represents the mini batch loss. In our neural network, we aim to minimize this loss function. So after training the network, we got the accuracy that reached to 82%, and it's stabilizing to be less than the training, which is non-adequate. We recommend the following step to gain better performance. So the first optimization will be controlling the learning rate. This is one of the challenging tasks that the learning convolution neural network. In our method, we schedule the learning rate by reducing the updating of weights by slowing down the learning rate initially to maintain the useful features. But then we speed up the learning feature. We set the dropout factor to 0.5 to obtain the maximum regularization. So for the first optimization, we found that the validation accuracy reached to 87.5%. As we can see here, the model is underfitting, which is non-adequate because it will lead the model to not learn enough patterns for the training data. So we will suggest another optimization, which is data augmentation, which is an automatically pre-processing stage during the training phase to cope with imperfect images in terms of different angles, substandard lightings, or not well cropped or framed images. This in turn will prevent the overfitting problem by showing the network different variations of the same images, like rotation, reflection, shear, scaling during the training phase. Subsequently, it leads to effortless adding multiple viewpoints of the same class. Hence, we will teach the network that minor shifting, mirroring, or cropping of the image will not affect the prediction, but it will enhance the classification accuracy. In another viewpoint here, it solves the problem that having few training data will be solved. In our method, we use AlexNet that expect the input images size 227 by 227 for the RGB image. So the training set should be first resized to feed the first layer. Besides that, we have added additional randomly vertically flipping and vertically and horizontally translating the images. We prevent the model from memorizing the training set. Also, we perform reflection and translating on the X and Y axis, so the dataset was augmented by 4, leading to 1,680 images effortless augmented of the dataset. We also shuffle the data before each epoch to avoid discarding it every epoch. So with this optimization, we found that the model is generalized, but the activation accuracy is still 88.7%. Now we'll combine the two optimizations as controlling the learning rate and data augmentation. We found that the model is generalized without any over or underfit, and the accuracy reached to 96%. by scheduling the learning rate and augmenting the data set, which is a very good model performance. Now we have another measure, which is the confusion matrix. By testing the 80 images, as we told here, about the 20% of the data set, the originally before augmentation. So the confusion matrix here is demonstrated. The confusion matrix is a numeric matrix that is used to measure the performance of the network by creating a matrix from the true class and the predicted class. We have here the 14 models of smartphones of 6 brands. So here it shows that how many observations in every cell. This diagonal of the matrix shows the correctly classified objects. The normalized row and column here display the percentage of the correctly classified class in blue and the incorrectly classified in orange. We found that the most of the smartphones here are correctly classified. And also this proves our accuracy that has 96.25%. Also, we can calculate here the loss function, which is how many incorrectly classified. We have here 3 in orange, 3 incorrectly classified out of 80. This is equal to 0.0375. Also here we have the loss function proved in this analysis. So now we are ready to implement the real test. So we conducted a real-time smartphone classification by using a light Gigi camera. This shows high testing accuracy here will show later has been achieved by using our transfer learning fine-tuned model. So this is, as you can see here, the accuracy 99% with different model orientation or rotation, and smartphone status broken. It leads to considerable result. So this confirmed our investigation that transfer learning does not require a massive data set to get high accuracy, even though the data set is small. We said that this is easier than building the neural network from the scratch, and training time is greatly reduced. So we can find here that the accuracy reached to 95-96% with different rotation and lighting standards. The result also here showed that despite having no information about the smartphone design, the model achieved good feasibility with high accuracy based on feature fusion by using transfer learning without having any information of the product design. Also, we have here different shiny and matte surfaces of smartphone models. So in this paper, we present how artificial intelligence could support automated smartphone recycling. Hence, it will act as enabler for circular smart cities. We investigate a feature-based extraction of smartphone to support circular economy. Currently, smartphone manufacturers endeavor to recycle their own products. However, their recycling programs are designed to fit their own products only. This may limit high recycling codes. Therefore, we develop a feature-based transfer learning approach It works without having any information about the design of the products. We use this transfer learning technique by using AlexNet as a pre-trained model to perform our tests and to gain the advantages of the transfer learning techniques as easier and faster than the training from the scratch, which we prove in our results. So by consequence, we conclude that AI and circular economy co-jointly be applied to achieve smart sustainability successfully, as we find that AI could help in transforming the e-waste management into a closed-loop system. This can pave the way towards circular smart cities. However, further research is needed. Smartphone recognition still faces some challenges even with the state-of-the-art image classification models, specifically the recent smartphone models due to the high similarity in visual characteristics. Future research will address these shortcomings. We suggest conducting non-destructive testing outside the visible light to detect the internal smartphone components. So we will show the battery, camera, ID sensors. This will help in material recognition by using fusion of sensors in different wavelengths to support automated recycling, hence to the circular economy. Last but not least, we argue that a fully sustainable system would require rethinking and the changing behaviors of customers and smartphone manufacturers. This will include for avoiding replacement of smartphones every couple of years unless they need maintenance, and thinking in maintaining raw materials needed by eco-design for future products. Thanks for your listening.
Hello everyone, my name is Alexander Krotin. I'm a third-year PhD student at Skolkovo University of Science and Technology, Moscow, Russia. In this presentation, I will talk about our work on assessment of video games players and teams' behavior by using sensing and data analysis. This is a joint work with my colleagues from Skolkovo University of Science and Technology, Anton Stepanov, Andrei Lange, Dmitry Nikolaev, Simon Abramov and Nikita Kluchnikov. The work is supervised by professors Evgeny Burnaev and Andrei Somov. The outline of the presentation is as follows. I will begin with some general introduction to electronic sports, and then I will cover the current research directions existing in electronic sports. In the main part of the presentation, I will share our experience of deployment of a system for data collection in a real-world electronic sports championship, and then I will provide some of our results of the data collected in this championship. In particular, I will briefly cover the results of heart rate and the voice analysis. Let me begin. Electronic sports, in fact, is just a competitive or professional gaming. Here, single players or teams compete against each other to reach a specific goal by the end of the game. Despite the recent popularity of electronic sports, a lot of people still think that electronic sports is not a sport. However, it is important to emphasize that electronic sports has exactly the same attributes as the classical sports. For example, electronic sports are competitive, so people play to win. Secondly, each player who wants to become a successful professional must have a professional attitude. This includes specific training regime and daily routine. Such trainings and daily routine have much in common with those of the classical sports. And finally, electronic sports are recognized worldwide. There exists a specific global association of international sports federations which takes part in all major eSports events and organizes a lot of electronic sports tournaments worldwide. In particular, in several countries, there exist specific local federations which are responsible for electronic sports, such as Russian eSports Federation in Russia. In general, it is important to note that nowadays the esports market is growing, so electronic sports attract more and more attention of amateur players and of professional players. This in particular means that electronic sports attract a lot of attention of researchers, which try to analyze the data collected from different electronic sports events, tournaments, championships, to provide specific insights on players' performance, on ways to win, on strategical aspects of the game, and so on. Let me cover current research directions in esports, but I will do it from a specific perspective of the data which is being analyzed to derive specific conclusions about the game or player's performance. One of the most popular type of data which is being analyzed here are the game logs, which are also called game replays or game demos. This is basically the recording of everything what happened during a particular game match, players' movements, players' interaction with objects and so on. Such data is widely accessible because for most popular games it can just simply be downloaded from specific online resources, which this data is stored, and almost everyone can just download it, parse it by specific tools provided by the developer, and then analyze it by statistical or machine learning tools and so on. This data is widely used mainly for game results prediction. There are a lot of research papers which try to predict who will be the winner of each particular match. Also, another popular research direction related to the analysis of game logs is the player modeling. This is also used by the developers themselves in order to better balance the game or to maximize the sales from specific downloadable content of the game. Over the recent years, a new direction appeared which is devoted to analytics and training of professional and amateur esports athletes. Several services appeared which provided tools to analyze in-game player performance and provide some recommendations in order to improve each individual player's skill. However, all these existing services mainly analyze the data which comes from the game logs, as we have discussed on this slide. And clearly, the data which comes from the game logs is limited in the sense that it records only what happens during the game, how player moves, how he interacts with other players or objects and so on. But it turns out that for a professional player to win, it is not enough to have a good skill and to properly collaborate with teammates. There are additional factors which significantly affect players' performance during the game, such as the psycho-emotional condition of the player. In particular, this is relevant for professional tournaments of high level, when typically one team wins another just because it has a better, more positive attitude to the game. All the existing research on the data related to the game logs does not provide any insights on this topic, simply because the data which is being analyzed does not contain any information about the psycho-emotional condition of the players. So to conclude, there is no available research or tools for esports professional trainers to assess physical and mental conditions of electronic sports athletes. So it is just the job of the team coach to assess it. However, such assessment is possible by using specific sensors which should be installed on the players when they play the game. Such analysis can provide additional insights on the concentration of the players during a long time period, or on additional psychological characteristics such as heart rate, which represents the tension, skin conductance, and so on. Also, sensors can be used to measure the reaction time of the players, especially in the stress situation. None of these characteristics can be measured just by considering the in-game data. This means that sensors can help in the assessment of esports athletes' condition. The research regarding this topic actually exists, but it is also limited. The main problem why it is limited is that to collect such data, one should create a specific conditions to collect this data. This can be done only in the laboratory when a specific sensor system is installed, and when the athlete plays the game, all these indicators are being recorded for further analysis by machine learning or other methods. The problem here is that collecting any data in the laboratory a priori means that this data will be small data, so unlike the game logs which can be collected almost from any match. Another problem of such approach is that the conditions in which the professional sportsman plays are quite artificial. First of all, it is not a real tournament match, and secondly, a lot of sensors may be discomfortable for the player, so his skill, his performance will be biased because of this tremendous amount of sensors. I would like to additionally emphasize that several research papers consider this kind of experiments in the laboratory with game players, but unlike the previous data analysis, which uses in-game data analysis, this research is limited because it is very hard to collect this data. And in particular, as far as we know, there is no research which studies the psycho-emotional condition data of the players during this professional tournament. And this is quite obvious why there is no such research, because it is extremely hard to collect data from the players which take part in such a high-level professional tournament during this tournament. There is plenty of organizational, privacy, and deployment of the sensor system issues which prevent such data collection. So typically the analysis only limits to the in-game data. So these are replays which are being analyzed, but again, they do not provide any information about psycho-emotional condition of professional esports athletes. The main feature of real-world tournaments is that they are actually exactly the same conditions which professional players have in practice. And there is no better choice than to assess psycho-emotional players' condition during the eSports competition better than just collecting the data from the professional competition. But as far as we know, there is no work which considers such a scenario. In our work, we actually consider such a scenario. We have successfully collected the data from the Electronic Sports Championship, and let me talk about this. First, roughly 2 years ago, in our university, an electronic sports laboratory and cyber academy was established. Its goal was to understand psycho-emotional conditions of esports athletes and collect relevant data sets for this analysis. In particular, based on this analysis, the goal is to create a recommendation system on improving skill and psycho-emotional conditions of professional athletes. And in particular, one of our recent projects is the innovation startup Headkraken about the analyzing of players' performance in game. This is probably one of the first precedents ever. We collected the data from Real World Championship on the Team Fortress 2 game and analyzed it. The tournament which we used to collect the data was the Team Fortress 2 Moscow LAN Championship, which was held in August of 2019. There were 2 days of tournament, and in total 7 teams took part in the championship. This means that there were 42 semi-professional players. Each team consisted of 6 players, and each of the players played roughly for 3 hours. We have recorded each of the players for roughly 3 hours. Let me briefly describe what is the game setting that players use to compete in. Team Fortress 2, the game of the tournament, is a first-person shooter game. 2 teams compete with each other. Each team consists of 6 players. Each of the players in the team takes a special role, and based on the role which he took, he obtains specific abilities, attributes and skills. In order to win the round, players had to capture specific points on the map, and the first team to capture all the points wins the game. This game mode is called Frontline mode. A team wins a round when it captures all the 5 capture points. A team wins over another team when it wins at least 2 rounds. The tournament was organized in the computer club in the center of Moscow. We set up our sensor system to collect the data from the players who took part in the tournament. Here I would like to emphasize that the players signed a specific document in which they gave us the right to collect and analyze their data for the research purposes. We consider 3 channels of data, that is audio, players' voices, their communication with other team members. This was recorded just from their microphones. We have also recorded the full game log of each of the games of the tournaments, and for some games we collected the heart rate of each of team captains. To collect all this data, we installed specific client-side software on each of the players' personal computers, which automatically collected all the audio data from their microphones and sent it by using local network to our storage. We also use the game server PC and send the game logs to our storage by using the local network. Heart rate was collected from team captains by using a wireless connection. To do this, we also set up a Raspberry Pi mini computer to collect data from the sensor and send it to our storage. So the players who took part in the competition did not feel any discomfort because there were no invasive sensors. Now let me move to the final part of the presentation about the analysis of the data that we have collected. Here I will cover heart rate data and voice data. Let me begin with the heart rate. First of all, we collected the heart rate data only for 2 matches. That was the semi-final match and the grand final match. In both matches, Team 1 competed. Actually, it was the winner of the tournament. And in semi-finals, Team 1 won over Team 3. And it then became the tournament winner in the grand final. Each of 2 matches consisted of 3 rounds, and to win, the team had to overcome the other team at least in 2 rounds. It turns out that the Team 3, which was the favorite of the tournament, actually lost the semi-final. After 2 rounds, the score between Team 3 and Team 1 was 1-1, which was quite unexpected for Team 3, but it turns out that in the 3rd round, Team 3 started losing very much to Team 1. This means that the tension drastically increased for Team 3, which is reflected in this box plot of heart rate of the team captain, which significantly increased between the 2nd and the 3rd round, when the team finally realized that they have little to no chances to win their opponent, despite the expectations. Analogous situation happened in the grand final. Team 2, unlike Team 1, was also the favorite of this tournament, but it turns out that this team lost to Team 1. After 2 rounds, similar to the semi-finals, the score between the teams was 1-1, and the winner of the 3rd round will become the winner of the tournament itself. It is clearly seen that the heart rate of both captains of Team 2 and Team 1 significantly increased in this final round. This is because the increasing tension of the round, because this in fact became the main round of the whole tournament. We also performed a much more detailed analysis of the player's voice. Here let us recall that our collected audio dataset contained roughly 60 hours of players' communications between each other. This is after all the pre-processing, cleaning and noise removing. To analyze players' emotions, we performed automatic labeling of emotions. To do this, we pre-trained a machine learning classifier on a different dataset and applied it to our dataset to label the emotions. As the dataset to train the classifier, we use the RAFDS dataset, which is a well-known dataset for speech emotion recognition. It has more than 1,000 recordings of 24 actors with 8 classes of emotions: neutral, calm, sad, happy, angry, fearful, disgust, and surprise. To train the classifier, we extracted from the raw signal male frequency coefficients, which are also widely used in audio data analysis, and we trained a random forest machine learning classifier on this dataset. Our preliminary analysis demonstrated that some of these classes that we used to train the classifier are not actually present in our collected tournament dataset. That is, disgust and surprise classes were very rare. Also, from the practical point of view, it is not reasonable to distinguish between neutral, calm and sad classes, because they all represent some kind of emotional passivity. Thus, we decided to remove the 2 classes from the training process and to merge 3 of classes into a single class, which we call calm. Thus, we retrained the classifier on 4 most promising classes, that is calm, angry and fearful, and we also additionally added a specific class called background noise, which was just manually collected recordings from our audio dataset, which represented the background noise. This was done in order to make our classifier more robust to additional noise which appeared in our dataset. We applied the classifier that we trained to our tournament data, and now we define a variable called emotional passivity. Basically, emotional passivity is just the fraction of time when each player was calm or silent. On the left here, you can see the comparison of the emotional passivity of players when they are a part of winning team and emotional passivity of the players when they are a part of losing team. From this plot, it is seen that the teams that win typically have lower emotional passivity, so they interact and communicate with each other more than the teams that lose the game. This difference is also confirmed by statistical tests. And this plot actually demonstrates that communication between the players of the teams is a key to victory. We also conduct an analogous comparison, but here we consider only the tournament winning team against all other teams. And again, here the same effect is observed. It is reasonable to conclude that communication is indeed a key to success. We also compare the attitude of players of different teams. We define the positive attitude as a fraction of time when the player was happy, and negative attitude by the fraction of time when the player was angry. On the left and on the right, you can see two bar plots indicating positive and negative attitude of winning and losing teams. As it is seen from the bar plots, the attitudes of the winning teams are much more positive than the attitude of the losing teams, which was quite expected. Analogous situation happens when we compare the negative attitude, and it turns out that the negative attitude of the losing teams is bigger than the negative attitude of the winning teams. This difference is also confirmed by statistical tests. Okay, to conclude our presentation, I would like to highlight two things. First of all, the deployment of the system for data collection in the real world championship is quite non-trivial. First of all, the preparation of the deployment must be perfectly organized in order to avoid any problems during the tournament. The problems of the system should not harm the tournament or the players itself. In fact, the entire deployment and each single sensor must be unobtrusive for the players, because it may have a negative impact on their performance. And of course, players do not want any sensors to have such a negative impact. Our data analysis demonstrates that players' tension increases significantly towards the finals, as it was expected. And in principle, communication is a key to success in team-based games. And as a quite expected consequence, we have that the communication of more successful teams is in a more positive tone than the communication of the less successful teams. This is all I wanted to show in this presentation. If you have any comments or questions, please contact us at the following emails. Thank you.
Thank you all for your participation. Now it's time to announce the Best Paper Award. Congratulations to Daniel, Khalil, Kevin, and Stefano for their paper, MOBIUS, Smart Mobility Tracking with Smartphone Sensors. I will then send this certificate to the authors. And to conclude, we look forward for other interactions with you in future editions, journal special editions. You can find information about them in the webpage of the conference. And that's it. Best wishes for you all. Bye.